Okay, so 20 minutes later, 20 minutes and 2 gin tonics later, no, just kidding. We are in the recap. We talked about clustering in the last podcast. Now we talk about classification, which is a supervised task. So now the patterns are called the classes, whereas in clustering the patterns are the clusters. Now the patterns are the classes, and the task actually is given a set of labeled objects. So objects where we already know to which class, to which cluster, to which pattern they belong to. We want to derive a model for each label, for each class, that can be used to predict the label of new data. So for example here you have the training data where you know those guys here are the A's and those green ones are the B's. So two classes A and B, and you want to derive a model where you can say if a new instance comes in, it's either an A or a B automatically. Yeah. So for example, here such a line between the B's, the majority of B's and the majority of A's would be such a model, because then you could derive that everything which is on this side of this line here is probably a B, and everything which is below this line is probably an A. Yeah, so that's the basic task, and since it's supervised, we already know a little bit about the patterns, about the classes, and especially some characteristics of these patterns, because we know already some training data. But of course, this is not complete. So there may be or the training data may be a bad example or bad sample. So there may be other training data which is much more important to derive the model from. So we have to take care that our model is not too specific to the training data, which means in that case it would overfit to the training data, but generalizes a little bit more, yeah? Because we are never sure that we see the right training data, or we see the entire characteristics of the patterns we want to discern now. And still, since we don't know, we cannot be too sure, we still need a lot of assumptions about how to model these characteristics of the classes, and how, especially how to differentiate between classes. So this is a model which is a linear model, so the boundary between these two classes, which is also called the decision boundary. Everything which is up there is a B, everything which is down there is an A. So this is a decision boundary, and here in this model we have the assumption that the decision boundary is linear, but that of course need not to be the case, especially if we have more than two classes. Most of the models, of the different models, have different assumptions about the decision boundary, how to differentiate between the corresponding classes. And that's again why there are so many different models out there, because they have all different assumptions about this decision boundary. And we will see next what is out there. But before we talk about the basic approach of classification, which is usually a two-step approach. We have a training phase where we build the classifier from the training data set, from the already known data set. And then if a new data set comes in, we have the prediction phase where we apply the classifier, the model, the rule to classify the unknown data, the new data. As we said before, the classifier should generalize rather than overfit to the training data. So the worst case is memorization of the training data, so auswendig lernen of the training data, because in that case, if we see something completely different which we haven't seen before, we are completely lost, yeah? Because then we just have to flip a coin or something like that, or make a random decision, which is more or less the same. So so that's why it's very important to generalize. And we, as we talked before, as mentioned before, we never know if the training data we have really reveals all characteristics. So we need or we target for a very generalized model. In order to avoid overfitting from the method by itself, we typically apply train and test scenarios for small training sample sizes. That means we don't want to evaluate how good our model is on the same set on which we trained the model. So because otherwise the memorization will always be the best model. So we split our data set in order to evaluate the trained model. We split the data set into a test set and a training set, and we train only on the training set and then evaluate only on the test set, which is different from the training set. That's important to avoid overfitting here. And in KDD1 also we talked about ensembles, where we combine several weak classifiers in order to improve the accuracy. And that probably makes sense because all those different classifiers have different assumptions on the characteristics. Some may be better for, I don't know, a given scenario or a given subset of training data, of samples, and some may be better in for another subset of the data. And then it could be interesting, or it could be a good idea to combine several classifiers in a kind of ensemble. So for example, random forests and boosting and stuff like that, those are ensemble techniques, and they are very often quite good actually, because they try to generalize again over several not so good classifiers in order to improve accuracy. So here are the basic classification paradigms. So first of all, we talked about in KDD1, we talked about base classifiers that model each class by a given probability distribution. Typically it's a Gaussian distribution, and prediction is then just done by maximum likelihood. So for example, here in a one-dimensional case, we have the blue class and the red class, and you see that the blue class is has this Gaussian distribution here, the red class has this distribution here, and this is the values we observe, which is the maximum speed of something. And well, if we have a maximum speed of 100, you see the likelihood being a red, red is high, risk high, being high risk is very low, and the probability of being low risk is very high. So we would pick blue in that case. And as you may remember, that base classifiers have the problem in higher dimensional spaces, that these the fitting of the probability distributions actually is not so easy in high dimensional cases. So in that case, to make it feasible, computational feasible, we had this attribute independence assumption, where we assume that the attributes, the features are independent to each other, which is in practice very often not the case. They are correlated, but naive Bayes assumes attribute independence. And the interesting thing, we talked about that in KDD1 also, is that this very bold assumption actually doesn't mean isn't too bad in real life. So naive Bayes is always a good baseline. Sometimes it's really bad, but very often it's surprisingly good. So naive Bayes is always a good baseline. Another paradigm is decision trees. So here is the idea, as you may imagine, partition the data set along attributes. So each node in the tree is a test among one attribute. So for example, we have the attribute car type, and the test is the car type of this object a truck? Then we go in this left subtree, or is it not a truck? Then we follow the right subtree. And then here in the right one is the question, is the age attribute, the value in the age attribute larger than 60, then the risk is low, or is it small or equal to 60, then the risk is high, and so on. That needs, in order to build up these trees, we need some purity measures. We talked about information gain, entropy, and stuff like that. Typically also it's an independent assumptions here, because we have axis parallel partitionings here, and we talked about the case that these trees have a very high tendency for overfitting. The tree itself is, I mean, it's a good classifier, but it has a very high tendency to overfit. So in practice, never use a single tree, always use a forest. So a forest is an ensemble of trees, conditionally independent trees. There are different ways to get that. For example, random forests had some randomization in here, so we get a forest of several, say 50 or even 100 trees that are conditionally independent, and the ensemble gives you a much better generalization as a classifier than the single trees, because the single trees just have they tend to overfit because they tend to memorize here. So the higher the tree grows, the more specific the edges get here, and the leaves, the more specific the leaves are, and in the worst case it's memorization. Yeah, then we had these linear models. Maybe you recall one of the most prominent things here are the support vector machines. So the basic idea is find a linear separation of the classes. For example, this maximum margin hyperplane of support vector machines, but there are other other concepts of linear separation. So the basic idea is you have two classes, and then you just split those two classes by a linear model. A linear, in two-dimensional case, it's a line. In a high-dimensional case, this is a hyperplane, a d-dimensional hyperplane. And last but not least, we had these nearest neighbor classifiers, the so-called lazy learners, or instant-based learning. You just use similarities or distance measures to training the objects. So you have the training objects here. The green ones are dogs, the red ones are wolves, and this one here you want to classify. So you just compute the nearest the object of the training object with the smallest distance, which is in this case a dog. So you say this one is also a dog. Yeah? So the class labels of the nearest neighbor or the k-nearest neighbors determine the prediction. Very simple approach, sometimes extremely efficient, especially in high-dimensional cases. Not such a good idea. We will talk about high-dimensional data in chapter 2 anyway, so we will see why it's not a good idea, or probably not a good idea in high-dimensional cases. So short summary on the classification part here. So as we said before, mentioned before, there are so many, or there are just very many more classification models out there, neural networks and stuff like that. So the models basically differ in the assumption on how to discriminate between classes, so which is actually the shape of the decision boundaries. Yeah? So you see here the shape of base classifiers are non-linear. Linear classifiers by definition are linear. Decision trees are these axis parallel splittings here. Nearest neighbor is also non-linear in some case. And neural networks, as you may know, are more or less, depending on which neuron or which type of neuron you use. So in the easiest case, it's a combination of such linear classifiers, which may look a little bit like this. So using several neurons or several layers of neurons ends up in very, very sophisticated nonlinear decision boundaries. That's a big advantage of neural networks. But of course, we talked about that in KDD1. The more sophisticated, the more complex a model is, and I mean the linear model is the most simplest model. The simpler it is, the less is the tendency to overfit. The more complex it is, the higher the tendency to overfit. And neural networks have a very high tendency to overfit because they have a very sophisticated and very complex model, very complex decision boundaries, and that's also why you need a lot of training data in order to really have a generalized model, generalized classifier here. Yeah, that was the classification subtask, and the next podcast will be about regression and frequent patterns, and maybe outlier detection. Let's see. So once again, stay tuned.